forwards and assume that part A, you can just look up. And I expect you can do that. So let's go to the next part. It says, derive an expression for the velocity of the free end of the rod at position B. Express your answer in terms of the physical constants and such. A lot of students had difficulty with this, even though this was done in class. In one sentence, write down why one of these is better than the other. I'm going to pick one of you. I'm going to pick a person I believe will struggle with their answer because I can see the look on your face. I'm not going to do that. I'm just going to pull one of you out of the roster. All right, Caden, can you tell me?
I'd say that energy creates a more direct relationship with velocity.
Um,
1/2 IW squared.
that may or may not be true. A direct relationship with velocity. I understand what you're trying to say. I'm not sure it's articulated exceptionally well, but it's not terrible. This question is about velocity, and I would always suggest you use energy when you're asked about velocity. But there's something else here that is more important. And so I want to see if you guys have that. Amanda?
It has a change of orientation.
No. Yes, sir?
Torque isn't constant.
That's it, right there. The torque isn't constant. Torque can't be used as a means of figuring out the velocity. Force, like torque, will give you an acceleration. If you remember when we talked about force beginning of the year, the only thing force can tell you is the size of an acceleration or the size of a single force. That's what force can tell you. Now, you could use acceleration to determine an object's change in velocity. This case, though, you couldn't, because in this case, the torque is changing. And it's more than just that. The torque comes from the fact that there is and here's where vocabulary is important, and you miss the differences. This object is experiencing a constant force. Weight. That force is constant. But it doesn't provide a constant torque, because torque is more than just the weight. When the bar has swung down to a position about here, about there, the force is still the same. It's acting at the middle of the bar. It's acting straight down. The weight of the bar hasn't changed. And the torque arm length hasn't changed. Both of those are the same, but the angle between the torque and the force has changed. And therefore, the amount of torque is different. In fact, in one of these problems, you're asked to graph this. How does the acceleration change as it swings downwards? It shouldn't have been a surprise that when it reaches its lowest point, the torque is 0, and therefore the acceleration is also 0. But I still had a bunch of people who tried to go to. If you went torque on this one, you lost all the points in the problem because you couldn't do any of the rest of the question, which took you from a potentially 3-point problem if you could do the calculus to a, 3 points total for maybe the calculus, and that's about it. Maybe a point here or there because you randomly wrote the right thing down. So we're going to use energy. Energy works in this case because the torque isn't constant. A similar, question would be like having an object roll down a ramp whose shape is curved. The acceleration would be different all the time, but we could still use energy to determine the velocity at the bottom. In this case, we can use energy to determine the velocity at the bottom. In this problem, I see two states of the problem, the before state and the after state. When we're here, the velocity, the center of mass, is moving. And there's several different velocities that you could be asked about. You'd be asked about the velocity of the end of the object, the tangential velocity of the rod at its end, or the tangential velocity of the rod at its center. But there's also the angular speed of the rod. Be prepared to answer any of those. We are specifically asked for, I believe, the angular velocity. Driving expression, the velocity for the free end of the rod at position B. They want this velocity. So let's give it to them. Rotational energy can't give me this directly. So energy can tell us how fast it's going. This is a rotating system. So if you guys don't recognize this, I can't find the tangential velocity directly. I can find the angular velocity directly. But if you didn't know that, you should probably write that down. And don't come after tutoring and say, well, how'd you know to use 1/2 I omega squared? I don't want to hear that question. Not because I don't think it's valid, but because I'm answering it this moment. This object is experiencing a torque. And because of that, it's going to be rotating at the bottom. The reason I know that here it's got gravitational potential energy is because the center of mass is at its highest point. And the reason I know that down here, all that energy is kinetic is because the center of mass is at its lowest point. I'm no longer talking about where the object is. I'm talking about where the object's center of mass is. So if you haven't gotten that down and highlighted that and reminded yourself that we're changing the discussion here, because trust me, it's going to get bigger than this. An object rolling down is going to change its location and its orientation. Are you prepared for that? If not, you need to understand this portion first. So down here, it's going to have kinetic energy for sure. But the system is fixed in place. Clear pivot point that doesn't allow the system to change location. But the center of mass is rotating through that point. So this is rotational kinetic energy here. So mgh equals 1/2 mv squared. This is not how the book does it. And you have to, recognize the book does change the potential plus change the kinetic equals change the potential plus change the kinetic. I don't do it like that. I just asked about what kind of energy do we have here compared to the kind of energy we have here. And is anybody going to correct me after that long tirade about using rotational and I wrote down translational instead? I mean, I would like it. I'd like somebody to say, you guys have no trouble interrupting me other times. Well, I guess you were waiting until I get 3 more steps away from there. So now I have to consider things that I do know. Height here being important above the top of this. That the object's height in this case represents the change in height of the center of mass of the system. So we're going to replace height with L/2. And now we're okay. So solving this for omega, I get mgl/I equals omega squared. Even if you couldn't do part A, you could have ended with this. This isn't the answer. This isn't what they were asking for. But I bet this is going to award you a certain number of points. Now you have more that you should do. We have an expression for the moment of inertia. We should use it. So that's where I would consider. Normally I would plug it in earlier than this, but I want to be clear. You could do this without known the answer to part A. But I do know the answer to part A. They gave it to me, 1/3 ml squared. So now I have that omega squared is going to be 3g/L. And yeah, we should probably take the root of that. Still not the answer. It wanted the velocity of the bottom edge of the rod as it passes through its lowest position. It wants the linear, the tangential velocity. They didn't use those vocabulary words. Tangential, I mean. It would be nice if they had, because it's a nice, clear vocabulary word that tells you exactly what they're looking for. But to get this tangential speed, we need to set that equal to omega times r. R is going to represent where along the bar they're asking for the tangential velocity. So in this case, I'm going to replace R with L. And you shouldn't leave it like this. Especially you guys who are not having difficulty with this. This is not the answer. Square the L, put it in the radical, and make this a better looking radical. That's better. All right. An experiment is designed to test the validity of the expression found in part B. Good. Can't wait. So I have a validity from part B. A student uses rods of various lengths that all have uniform mass distribution. The student releases each rod from the horizontal position and uses photo gates to measure the velocity of the free end at position B. The data are recorded below. All right. So I've got a set of data that has length and velocity. Leave you with a couple of spaces here for you to prepare your data. Fill out the chart, plot the answer. I have no intention of doing the rest of the problem, the graphical portion of this problem. It's really outside the scope of this unit. It's something that encompasses all units. But this was 2015, and you were asked to do it then, so it's quite plausible you could be asked to do it now. This is well within the confines of our current state of the exam. Indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity. So remember, our velocity was equal to the square root of 3gl. Now, this isn't a question that has to do with rotational motion or energy or torque or anything like that. It's not even a moment of inertia question. It's a lab question. And it's one that involves linearization of data. You have two methods for linearization. This one seems like the right method to use, solve for your variable. And that's what I'm going to do. I'm going to square both sides. Now I'm going to solve for G. And it looks to me like the best choice would be on the horizontal axis to put 3 times L, on the vertical axis to put V squared. Of course, you could just put L and V squared. That would probably work out just fine. And there are other ways you could do it too. This is just the way I'm teaching you. And they were kind enough to this is from set 2. There's always 2 versions of the exam floating around, and set 1 I think was easier than set 2. The bent rod is it's never been done before. It's the first time it's ever appeared in the exam, and I think it was different enough that students were spooked by it when they saw it. I would not have used it as a test question, as a training for helping you guys, prepare for the exam. I would probably have used it as a review question later in the year, or in the capacity that we're using it right now. Aside from that, question A, I'm putting it on there on purpose. I want you to understand they ask it pretty frequently, and last year's no exception. So I don't want to do this one because it's just a regurgitation of what's been done before. They say specifically, though, to use integral calculus. saying that because you could have just said, well, a bar is 1/3 ml squared about its ends. So can I just substitute in 2L here? In some years, they would have accepted this. That's why they got Y's in the last couple of years and made sure they said show using interval calculus. By making that statement, you can't show it this way. You have to do the interval calculus. And the only difference between what we did in class and this one is you just set your limits from 0 to 2L. That's it. And I think we get m over L x squared dx. So just set your limits. Yes, sir?
Yeah, that's the 2L for M over L.
Oh, this should be 2L2 probably. This should be there. There, yeah. That would have to be 2L as well. Thank you. Now, you could have left it M over L, and then at the end, after you showed through interval calculus that it's 1/3 ml squared plugged in 2L, you could do that too. They gave credit for both. But it's really not much of a difference. And you never use it again, right? So even though we did all that work, it's kind of useless because the next question says, all right, given object B. Oh, goody, object B. Object B of total mass M is formed by attaching two thin uniform identical rods of length L at a right angle. Object B is held in place as shown above. Express your answers in part B in terms of L. Determine the following for the given coordinate system found in the figure. They want the center of mass. As questions go, center of mass of this piece isn't horrible, really. And I even talked about a method for doing this, but I'm not. I saw some of your work, and there were some interesting things out there. Some of you, I think, just looked it up. Really? Come on. You can do this. One way to do this is to treat it like two point masses. It says it has uniform density. So the center of mass of each bar is at each bar's middle. This is how I suggested doing it for the one where we bent this thing in a circle. Remember, I bent it into a U. I just recommended using the center of mass of each piece. Now, if you're feeling super fancy, we've not done it this way, you could do integral calculus to determine the center of mass. I think that's a little overkill and wouldn't recommend it because it's so much easier to do it this other way. So let's do it this other way. X center of mass equals the summation of mx over the sum of m. In the x direction only, there are two contributions to the center of mass. Starting from here, the first contribution is there, and that is mass m located L over 2. The second contribution to the center of mass is found right there at the end. That entire bar acts at the end of the rod. So its contribution is just ml. We're treating them like point masses. And all that matters in the x direction is where they are horizontally. Divided by total mass 2m. Yep.
Doesn't each of those bars only have a mass of 1 over 2? Or each point mass?
Object B of total mass m. All right, I read that wrong. So it won't affect the answer, but we should do it anyways to be correct.
If you have put M
they'd give you full credit for it. Because your answer doesn't have M in it anyways. Unless, and be careful, I mean, they could have said that the bend was one mass and after the bend was another mass. So you want to be careful about that. But being that we should be accurate, we should do it this way. All of these just cancel out anyways. You're left with L over 2 plus L divided by 2. So L over 2 plus L is 3/2 L. And then 3/2 L divided by 2 is 3/4 L. And I see no reason to redo that for Y. Right, symmetrical. I mean, I see no reason to, but does somebody want me to do it again for Y? So that means center of mass is like right here. Right, 3/4 of the way on both. Now, it's a weird question. Not terrible. So we've got B done. This distance from here to here is less than 2L. So when we look at the distribution of mass away from the pivot point, it's not as far away. Same mass, closer to the pivot point, it's got to have less moment of inertia. Yep.
Could you also say, like, since the center of mass is closer to the pivot, would that be a reasonable explanation?
I would be very careful about using the center of mass explanation, as the distribution of mass is so skewed by the location of the mass away from the pivot point. I mean, that L squared just skews it too much. All right. Next. Object B has a rotational inertia of I. I don't even have to find the rotational inertia. Well, I think that's a disappointment, because I think you could have found the rotational inertia. In fact, I would have liked to see you guys find the rotational inertia. And I'm thinking perhaps I will force that to be something I see that you guys can do. It's just 2 bars. I think you can find the rotational inertia of each individually and then add them together. So we will face that problem here in a bit. But is the value of IB greater than, less than, or equal to IA? I really hope this wasn't a difficult question, but I read your answers, so I kind of know. And the answer should be because it doesn't actually, the mass isn't distributed as far away from the pivot point for object B as it is for object A. It's all about distribution of mass, not the mass itself. And when we look